Great. Thanks so much. Thanks so much for having me here. And yeah, I think my talk does complement Randall's. As was mentioned, I used to work for Microsoft for a number of years, where I worked from the perspective of the publisher, and I spent a lot of time trying to model advertisers and think about pricing, a lot in the spirit of a lot of the talks this morning. More recently, I'm on the board of Expedia, and I'm on the board of a couple of startups, and we're spending, especially like Expedia, like Netflix, is spending hundreds of millions of dollars a year as an advertiser. And so I've been thinking about those problems a little bit from that side as well. And then in my scientific life, I've started working more on filling in, I think, some of the foundations of the statistics and econometrics and machine learning that have been missing when you're trying to bring kind of big data tools to causal inference problems. And in some sense that there were I'm going to be a little bit different than Randall in the sense that he was kind of showing you an end-to-end system, which kind of shows you, I think, like the state of the art. Like I think that probably Netflix is the best advertiser in the world in terms of, you know, how sophisticated they are in terms of doing causal inference. He's also shown how you can implement some of their tools very simply. At the same time, you know, there's a huge heterogeneity of advertisers, just like there's actually a huge heterogeneity of research perspectives on all of these things. So the work that I'm going to show you today is kind of building up almost from much more basics and trying to fill in some of the theoretical gaps, as well as, in some sense, give tools that you might use as your sort of first pass. Like if you're moving away from just pure correlative models, which a lot of advertisers in practice use, you know, what are some of the first steps away from that? So we're kind of meeting in the middle with Randall's talk. One of the themes, actually, I do want to highlight from Randall's talk, which is something that I'm also exploring in work I won't talk about today, is that, well, I guess a higher level theme is that in the real world, we often don't have enough data, we don't have enough statistical power to do things as perfectly as we would like from a causal perspective. Like in some sense, there's a very simple answer to how do I do causal inference, which is, you know, I have a treatment group and a control group and I compare things. But a lot of times that's too noisy. And so there's a general challenge, which is how do we use all the data that we have? Maybe we've been watching these users over time. Maybe we've been watching lots of ad campaigns over time. How do we use all the data that we have to make the best possible decisions? And so I really like Randall's entry into that kind of agenda. And that agenda from a theoretical perspective is actually not very well formed at all. So I would predict, though, in 5 years, there's going to be a whole literature you know, of which Randall's papers will be, assuming he gets to publish them, will be early entries. And assuming I finish mine, there will be other early entries. Okay, and so I just want to, so I'm mostly publishing right now I'm actually focusing on the sort of statistics journals in terms of where I'm publishing stuff. So following that tradition, I'm posting all my papers on arXiv rather than in the machine learning conferences. So if you look me up on arXiv, you'll see all the papers that I'm going to talk about today. Okay, so the general kind of topic, and something that I think is just incredibly exciting from a scientific perspective, is this new intersection of using machine learning for policy and scientific understanding, not just for prediction. And of course, I don't want to say just prediction. So actually, guys in the back, there's a bunch of room on the floor. So if you can climb over these two people in the aisle, there's room for at least like 7 or 8 people on the floor up here. So maybe the people in the aisle can like move over and let a few people crawl past them. Okay. So as I was sitting on the floor in the last session, I'm appreciative of the ability to sit on the floor as opposed to stand in the hallway. So, you know, and I have to say that, you know, in my career, I've worked on a lot of different things. I've worked on mechanism design. I've worked on games of incomplete information, dynamic mechanism design, things like that. But this moment is actually a really exciting scientific moment because we have a whole set of new questions that's been opened up. These questions are coming out of industry. They're coming out of these big data applications to which we don't have the scientific answers. And so when I think about, you know, machine learning has had all these breakthroughs algorithmically, but it's tended to neglect causal inference. And when I have to go out to people, probably everybody in this room has thought a lot more about correlation versus causality, but one of my favorite examples of just trying to say where you get different answers is that why have economists thought so hard for so many decades about causal inference? Well, if you take a data set that has prices and quantities in it, okay, like one of the fundamental objects in economics is the concept of a demand curve. And a demand curve is basically the idea, it's a counterfactual object. It says how much would you sell at different price levels. And so like 50 years ago when we first started to be able to run regressions, sometimes you'd do it by hand, but you had little guys inverting matrices, but you would take a data set with prices and quantities, and the first thing you see is that it slopes the wrong way. That is, it looks like in almost any economic data set, higher prices are associated with higher quantities. If you think about if I had a data set of hotels, suppose you had a data set where you had prices and quantities. If I told you that the price was high, would you predict that the hotel was empty or full? Well, anybody who tried to book a hotel this week would say, hey, the price is high, I predict the hotel is full. But you obviously can't use that for policy. It's not the case that if you raise your prices, you will sell more hotel rooms. So we had to deal with this problem. It wasn't like, oh, just maybe it's rounding error, maybe we can ignore it, because you literally get the wrong answer. It's just completely useless. And so economists worried about instrumental variables and things like that a long time ago, because without it, we just couldn't write a paper, basically. We couldn't do our science. So another example, that's very common in the online advertising space is thinking about the contrast between identifying, say, units at risk versus those with a high treatment effect. And here, at risk would mean risk of a conversion, risk of a click. So even you talk to the big advertising platforms, you talk to Facebook and you say, hey, tell me about your great tool. And like, oh yes, I can tell you exactly where to put your ad. I have this fancy dancy tool. You say, well, what is the tool optimized for? Well, it optimizes for clicks. Okay, so if you sign up on Facebook and say personalize where my ad should go, it's going to put it against the consumers who click the most. But of course, the consumers that click the most may be consumers that already knew about your brand, and that's totally not what you're interested in optimizing for. And so, when I talk to economists, they're actually kind of stunned that this entire industry is still operating on spending billions of dollars using non-causal estimates, and that some company as sophisticated as a Facebook or is going to be telling you how to spend your money in a way that might be completely orthogonal to your interests. As Randall mentioned, for some firms, the click is the same because all these firms that are showing you about new products, that may be totally fine. But if you're Expedia spending hundreds of millions of dollars, people have heard of Expedia, and it's probably not the same. So I have a recent perspective piece in Science that talks about some other issues in this area. So what we don't want to throw away machine learning, even though it's mostly focused on prediction, because machine learning has so many advantages. It helps us build more granular statistical models. And so we have a small but growing literature among a bunch of us between statistics, econometrics, and machine learning that's working on these problems. And some of the themes that have been coming out of this literature are that machine learning can improve the performance of traditional causal inference estimation methods. And again, we've been doing those methods for about 50 years, but they've been they've been somewhat successful, but they're also sort of controversial in a variety of ways because sometimes results aren't robust and things like that. So what are some of the ways that machine learning has been able to improve the traditional causal inference estimation methods? First of all, the better use of observables to control for confounders. So it's often the case that your methods only work if you control for a lot of stuff, and you need to control for it well and flexibly. Traditionally, in econometrics and biostatistics, we hand-tuned our models. And that obviously is not state of the art, and it also led to lots of wars about, I get a different result for the effect of the minimum wage than you do, and it's because of the functional form that I used, or different effects of charter schools and so on. These things you read about in the paper about the effects of the minimum wage, the effects of charter schools, are a lot of times using these types of methods. A second thing is that machine learning, as we know, makes more granular predictions. That is, we might have even personalized predictions. And so what we would like to do is be able to have personalization in a causal inference framework. One of the challenges there, though, is that if I'm making a personalized prediction about you and your counterfactual states of the world, Well, it's hard to have a model-free way to assess performance because there's no one quite like you. And I only saw you with an ad or without an ad. And so one of the beauty of machine learning methods is that you can use cross-validation, you can hold out a test set and see how well you did. But if everybody in the test set was only seen in one counterfactual state of the world, I don't know how well I did, at least without using a model. So it's trickier to understand how well you performed. And so dealing with that has been another theme of this literature. I won't spend a lot of time on that today, but it's something that we've all been worried about. Broadly, if we get more granular statistical models, we can have a better understanding of how and why a policy works for continued improvement. So one place where this new methodology has gotten used in practice just in the last 2 years is that various tech companies have put into their A/B testing platforms the ability to look for heterogeneous effects of an A/B test. And so if you're an engineer building an algorithm and then you A/B test it, you want to understand not just, did it increase clicks by 0.2%, but you want to understand for whom did it increase clicks and for whom did it decrease clicks. So that helps you go back and fix your model and find where to improve. But of course, you want to do that in a way that's reliable if you don't want to just have some spurious result driving your engineering effort. So we want to have reliable ways of understanding when something works. And of course, in advertising, we want to know for whom individually did it work, and ultimately we want to have policy assignment rules for who gets what ad. So Randall did a great job introducing this concept of correlation versus causality in advertising measurement. The question, did advertisement cause the sale or would the sale have happened anyway? I don't think he put like the final numbers from the Blake, Noskow, and Tadelis paper, but roughly like the eBay search campaigns using experiments had a minus 63% return rather than a 1,500% return, which is what you would get using the standard methods that were non-causal. And so the best solution is A/B testing or maybe bandits and really building a full production system, which I think Randall is on the cutting edge of that really uses causal inference in everything you do. But for many firms, you're a long way away from that. And so what you would like to do is be able to do something a little more in between. Like maybe you're going to run 10 A/B tests a year or 20 A/B tests a year. And then you're going to make a lot of operational decisions without having the holy grail of a fully causal system that does automated bidding. And so one of the heuristics that I see advertisers use in practice is that they are going to use some of the methods like I'm going to talk about today that are methods designed for drawing causal inference from observational data, non-experimental data. Then they run A/B tests to see how well those methods do. And for some advertising platforms and some types of ads, those methods may actually do pretty well so that the observational models look like the A/B test experiments. Or maybe they're off by 10%. Then you just apply a 10% haircut and use your observational method, which is much more precise and easier to make personalized decisions and break out more finely and so on. So what I'm going to talk about today are what are the best-in-class observational methods that you might be able to use in conjunction with A/B testing. Again, though, I think ultimately where we're going to get to in 5 or 10 years is something that in real time combines the observational and experimental data the way that Randall suggests. So I'm not arguing that where I am today is the ultimate holy grail for us, but it's a stepping stone along the way. And then the research I'm going to talk about is mostly like it's theoretical. So we're publishing in the top theoretical stats journals and we're providing the foundations for these methods, which ultimately we will bring the theory up in line with the kinds of work that Randall is doing. So basically the practical solution is use best available observational methods, validate these observational methods by comparing to experiments. There's another thing which I won't really be able to develop fully today, but I've been pushing in a series of papers, is the idea of using supplementary analysis to validate the approaches. So a lot of times these observational methods require some assumptions, but those assumptions can be tested and validated. The causal inference literature historically didn't put as much emphasis on that because they often had like one experiment. So the causal inference literature was set up for like Seattle raised its minimum wage. They did it once. We're going to evaluate it. So that we're kind of stuck with that. And it's very hard to assess your assumptions when you have just one city once. But in the tech world, we're doing changes all the time, and we have lots of little experiments. And so this is another interesting new scientific area to come up with systematic methods to assess your performance of your model, taking advantage of the fact that you have lots of small experiments. And so the two examples I'm going to talk about today are techniques based on unconfoundedness and instrumental variables, which Randall was focused on instrumental variables. There are a few other techniques that are commonly used in the causal literature. Things like difference in difference and regression discontinuity are the two other big approaches. Difference in difference gets used in practice all the time. You're watching one group over time that was exposed to a campaign and another group that wasn't, and you use the group that wasn't to control for the time trends. We're also doing machine learning methods in those areas as well. So if we want to improve the existing causal inference approaches, what are some of the big things we're trying to do? Well, those traditional things suffered from non-robustness. There were lots of wars in economics about what the right answer is. People would take the same data set, and one would say the training program worked, and one would say it didn't. And that was because the results were very sensitive to functional form, and you had to argue about the validity of your method sort of based on reasonableness. So what we want to do is use machine learning methods to have a data-driven approach to select the functional form, but, big but, we need to modify machine learning techniques to optimize for causal inference versus prediction. And so there's a bunch of reasons why those are very different problems, and that's been a big theme of it's given us lots of new theory questions to answer. One very simple thing is we want to avoid regularization-induced bias. So if you think about a simple example where I'm using a lasso to run a regression, and I want to use regularization to shrink the coefficients on some of the x's. Well, if I'm trying to do causal inference, so I'm trying to look at the effect of y, a treatment on an outcome, and I have a bunch of control variables, normal regularization is going to regularize probably too much. Because in order to get an unbiased treatment effect, you need to make sure you control for all the confounders. You need to control for everything that's related to both the treatment and the outcome. And just throwing things into a lasso is going to focus on just what x's predict the outcome, but it's not going to care about whether the x's are associated with the treatment. So that's an example of where you want to use a different objective for prediction versus causal inference. Another thing that is very important in the causal inference literature is getting centered confidence intervals, asymptotic normality, and efficiency. One of the funny things that I observed in tech firms is that we have this huge schizophrenia. On the one hand, we use kind of black box machine learning methods to develop algorithms. On the other hand, we put them through an A/B testing platform and where we care very much about unbiased and statistically significant results. So what I'm looking for is a machine learning method that's going to give you personalized estimates, also with centered confidence intervals and the ability to say that this result is statistically significant. Okay. So let me introduce a little bit of notation. So I'm going to use the potential outcomes framework, which is the framework that has been used for the last couple of decades in a big part of econometrics, statistics, and biostatistics. And the potential outcomes framework is a really nice way to talk about counterfactuals and also to talk about estimation methods and compare estimation methods. So we're going to have a feature vector x, a response vector y, and a treatment assignment. And for today, this treatment assignment will be binary. Did you see the add or not? And so we posit the existence of these counterfactual quantities, these potential outcomes, yi of 0 and yi of 1. And the idea is that for you have a certain heart rate if you had a cup of coffee. Everybody noticed the coffee was gone. You have another heart rate if you had only the tea that was left outside. So, so each person has a different state of the world depending on whether they had a treatment, but I only get to see you within the state that you were in. So this is really kind of a missing data problem. For every person, you have a vector of potential outcomes if there's multiple arms, but I only get to see one of them. And then if the W is related to your potential outcomes, like if you drank coffee because coffee gives you a big boost, and you don't drink coffee because it gives you a stomach ache, then I can't just compare the coffee drinking people to the non-coffee drinking people. So we can, in this context, we can define two objects of interest. And actually, how can I get rid of that? Oops, no, that didn't get rid of that. Sorry, I don't use a Mac. All right, there we go. So three potential objects, actually. The average treatment effect is just, what if I gave everybody the ad or I didn't give anybody the ad? That's the difference between those potential outcomes. The average treatment on the treated is, well, what was, for the people who did see the ad, what was the effect of the treatment on them? So that's conditioning on WI equals 1. And the idea is that I might have done this experiment on a population that the people who were treated might look different in terms of their observable characteristics than the control group. And then finally, the conditional average treatment effect is conditional on your personal characteristics. What's our best estimate of the treatment effect? So for personalization, this is what you want. If you are just trying to see, like, should I roll out a TV campaign, or, you know, should I introduce a product, or should I raise the minimum wage, something like the average treatment effect is the right object. I probably won't get to it, but at the end of the talk, and you can see on my papers online, I actually show in some other work that when you're thinking about estimating an optimal policy, the literature on average treatment effects actually becomes important, because you can think about the policy not as just being showing everybody the ad, but you can actually think about an algorithm that assigns each person to an ad based on their characteristics. You can think of that as a policy, and you can think about evaluating, what if I give this algorithm to everybody or I don't give the algorithm to everybody? So the average treatment effect literature is relevant to you even if you're doing personalized allocation. Okay, so just to kind of, I have a lot of words on my slides, but I have to throw in a cartoon here and there. So here's an example of thinking about causality. Just my stomach hurts. Maybe it was a bad tuna I had for lunch. Too bad I don't have a proper control group. Now I'll never know. And I think part of the thing that the cartoon doesn't say is that, you know, I'll never have a proper control group for myself. I won't know whether my stomach would have hurt or not. And so we might be able to learn if for a population or a population of people who look like me, whether the tuna gives you a stomach ache. But for you personally, I will never know. Okay. So if we make no further assumptions, it's not possible to estimate any of these quantities. And I think something that is very much drilled into the first-year econometrics students, but I think sometimes I argue about with machine learning people, is this concept of identification. So it's not that we don't have enough data. It's that even if I had an infinite amount of data, if I don't have additional assumptions or additional type of experimental variation, I will never know. And so it's just going back to the hotel prices and quantities thing. If I could have a huge data set of hotel prices and quantities, but if in that data, prices and quantities are positively correlated, I'm going to continue to find that with an infinite amount of data. When you think about what kind of data might help you solve the problem, it's not just having more observations of prices and quantities, it would be having observations of other stuff. Maybe I could observe everything, if I wrote down every convention that ever came to town and everything about the weather and things like that, and airline prices, maybe I could build a model that would explain everything about why people want to come to a city, and I could sort of control for some of these confounders, like the fact that KDD's in town caused the prices to rise and it caused the occupancy to explode. Okay, so it's not about the amount of data, so we have to make assumptions. Of course, the simplest assumption would be that the W's were randomly assigned. I'll still call that an assumption because you can randomly assign, I could randomly assign each of you coffee, okay? But it's still an assumption that I carried out my randomization correctly and so on. So if you have experimental data, you're making an assumption, but it's a very well justified assumption that, like, your engineers implemented your randomization correctly. Another type of assumption is that we have measured everything that was important to the treatment allocation. So this condition here says that conditional on the observable characteristics of the individual, the treatment assignment was independent of your potential outcomes. And it's important to write that in terms of potential outcomes, because what you want to say is that I didn't get coffee because my yi1 minus yi0 was big. So the type of thing that happens when people get to choose their coffee is that the people for whom the gap between yi1 and yi0 is big, that is, they have a big individual treatment effect, buy the coffee. So it turns out with that assumption plus overlap, where this E of x, which is the probability of being treated as a function of x, is never entirely 0 or 1, we actually can identify causal effects and estimate them. And it's basically just saying that, well, conditional on x, the treatment is as good as random. So there's lots of reasons why this would fail to hold in advertising. But there are also many applications where you think it might hold. So just as an example, suppose that you have an algorithm that's allocating people to advertisements based on their characteristics. Say you're actually inside Facebook, and you have the log data of all the characteristics that go into that algorithm. But you also know that at Facebook, you're running A/B tests in the background, and glitches happen, and servers update at different times. And so, in fact, it's not completely deterministic who gets an ad as a function of their characteristics, but you actually observe all the characteristics that go into there. Then, in principle, you can come back and do this. Now, you might say, well, gosh, if you're inside Facebook, you know the whole algorithm. So why don't you just write down a model of the entire Facebook production system and just use that? And of course, I worked at Bing. Yes, I could have read all the lines of code and tried to actually write down exactly what was happening, but the fact is that it was a moving target. It wasn't written down. A lot of the algorithms themselves are black boxes. So even though you have access to everything about the actual assignment process, you still end up in practice wanting to use statistical methods to describe it because it's sort of undescribably, it's too complex to be described. So that's the type of setting where I think these techniques make a lot of sense. You're working for a publisher, and the publisher is, showing different offers to different people at different times, and you know what the buckets are that led different people to get different things. Yeah.
So the unconfoundedness, does it mean that given if I know all the characteristics about the person, the treatment effect would be independent of the actual treatment?
Yes. So it's basically saying it's as
ad versus I don't show you ad.
It's as good as randomly assigned if I know everything about you. Now, you might argue, and this is one reason this is controversial in economics, is you say, well, if I really know everything that's relevant, why is there any randomness left? And so, yeah. And so I think that in some cases, that is an incredibly compelling argument. So you have to be very careful about your specific setting. So when I tried to look at these types of things at Bing, I knew some sources of randomness. I knew we had different servers updating at different times. We actually had randomness built into the budget allocation algorithms. So we had specific sources of randomness that would randomize even conditional on your characteristics. But if you don't, if you're bidding into it, suppose you think, oh, I'm going to do this in my Facebook bidding or my real-time bidding system, and I'm going to think about, everything that controls whether I bid. Well, whether the person saw the ad conditional on you bidding is certainly not as good as random, because the reason that some people don't see the ad is because other people bid on them. Okay, so that's a huge violation of this assumption. Probably one of the there are many, but that's one of the really important ones in ads. So I think that this type of method does have a bunch of great applications in the advertising space, but you have to be very careful with it. And so, one of the things we could do as a group is that we could try to get publishers to create tools that make use of their internal data that would allow us to be able to do this type of exercise. You couldn't do it today if you were bidding on Facebook or something else, because they're not giving you enough data to know how to apply these methods, but they could possibly build such tools for us. Yeah, well, so I think, again, that all of those things are confounders. And so the idea of when you might use this is, suppose you had a really rich model of the user's interest, then you might be able to control for that and find two users with the same interest. Maybe the article posted at 2 p.m., some people came at 1:30, some people came at 2:30, they had the similar past interest, so it was basically random whether they came at 1:30 or 2:30. Those are the types of designs you have to use, but you have to use them carefully. So what I would say is that there are certain settings where the assumptions hold perfectly, but those assumptions generally occur when you're working inside a publisher or when you have access to a lot of information, you have more control about it. then they're going to work imperfectly in other settings. And that's where, you might use these methods to get closer to a causal estimate, but not entirely to a causal estimate. And then you might once a year do an A/B test and see, and then maybe you're taking a 10% haircut instead of a 100% haircut on, so you're going to get closer to the truth, but not all the way there. Okay, so there are a bunch of estimation methods that work, and actually one of the challenges of the econometric literature, the small data literature, was that there was a bunch of methods that all theoretically worked equally well, but they actually worked very differently in practice, and which one worked better depended on the application. So that led to a lot of debate and really criticism of this whole literature. So when I think about small data, I mean that I've got a fixed number of covariates, and I'm thinking about taking the number of observations to infinity. That's what I mean by a small data world. Some of the methods that people used, one of the most popular was propensity score weighting. It was recently actually at a retirement party, a birthday party for Hal Varian, and a story was told there about how somebody on Hal's team presented to Eric Schmidt about propensity score weighting, and then another team came in later in the day, and Eric Schmidt said, well, how did you separate correlation from causality? And the team said, and then he said, well, why didn't you use propensity score weighting? Go away and don't come back to my office until you've used propensity score weighting. So that's the danger of educating executives, I guess, about causal inference. All your team members will hate you. So propensity score weighting is really a very simple way of working on this. And this is the way that I think has gotten a lot of traction in the machine learning literature because it feels very familiar. So there's a general idea in machine learning that you might have a training data set that has one population, and you want to apply that method to predict things for another population. So a simple thing you can do is try to reweight your training observation to make it look like the observation upon which you want to predict. And that's basically the insight of the propensity score literature. And so Donald Rubin and co-authors developed this theory in the 80s and really kind of formalized it. But the basic idea is that you estimate the propensity score, that is your propensity to be treated. So as a function of your characteristics, how likely are you to be treated? And then I weight you by the inverse of that propensity score. And so the idea, if there's some people with certain characteristics that are very unlikely to be treated, well, I'm going to upweight them when I think about applying to estimate what would happen in the treatment group. Another method is just a direct model of the outcome. So here is just basically you build a predictive model of y on X and W. Using regression, you could use lasso and so on. And so one of the insights of the recent machine learning and causal inference literature is that if you try to do this in high dimensions, not only is it not effective, but it gives you badly biased results. So this is a bad idea in high dimensions. The idea that this works is based crucially on the idea that you know the x's and you know the functional form, and you're not using regularization to pick the functional form. The problem being that if you're trying to control for x's that are confounders, regularization is going to zero out some things that were important to control for. And then a final thing is very popular is double robustness. So you run a regression of y on x and w, but you weight the observations by the inverse of the propensity score. And so this is doubly robust in the sense that if you make mistakes in one of either the propensity score model or in the regression specification, you still get the right answer. The choice among these methods is widely studied. There's actually a bunch of other things too that are not efficient econometrically. That is, they're not the minimum variance estimators, but they often do better in practice. And which one is better depends, and that's been controversial. So when I think about advertising effectiveness and the specifics, we want to think about what is the problem you're trying to solve, first of all. Well, the big problems, the user saw the ad because of an action they took indicating interest in the product. Like I typed eBay into Google, that's indicating interest in eBay. And so seeing an ad is the person who sees the search ad on eBay is very different from the person who didn't, because the person who saw the ad typed eBay into Google and they were going there anyways. Or, as Randall pointed out, and they've coined this term in his team, the activity bias, users saw the ad because they were active on the internet that day, and you can't spend money on the internet if you're not active on the internet. And so just seeing someone on the internet is a huge positive signal that they're going to spend money on that day. And both of these things are just massively important, and they can turn an ROI of a campaign from plus 200 to minus 200 by correcting for them. So they're hugely impactful quantitatively. So to solve this problem, I want to adjust for confounders compared to individuals for whom the ad assignment was as good as random. And so one of the problems is it may be that suppose I actually got inside Facebook and I got Facebook's beta and I saw every attribute that Facebook was using to determine who saw the ad, that would still be a very high dimensional model. And so I still actually wouldn't know what to do even if I had all of Facebook's data. Okay, so how are we going to solve this? Well, it's easiest to kind of describe this if the true model is linear. So suppose that if you're a treated guy, your mean is your x's times some coefficients beta of w. So there's going to be one set of coefficients for the treatment group and one set of coefficients for the control group. And this x will include a constant. So for example, the treatment group and the control, if there's a constant here that depends on w, then getting the treatment just might increase your mean outcome, and that's incorporated in that model. So if we're trying to estimate the effect of the treatment on the people who are actually treated, and that just simplifies the algebra a little bit to focus on that group, the average treatment effect on the treated is the mean outcome for the people who actually were treated minus what I think would have happened to those people or to people who looked like them if they had been in the control group. And so if I think about beta hat of 0 is my prediction for what would happen in the control group, what I'm trying to do is say if people who looked like my treated group were in the control group, what would have happened to them? And so if I think about what's the difference between this estimate and the truth, well, if I'm in a small data world, I can just use a least squares regression for the fixed x's, and I can get an efficient estimate, which converges at the rate 1 over square root of n. So the natural thing to do would be to substitute in a lasso, a ridge, or elastic net, but bias is a big problem. There's two problems, actually. One is that just each individual coefficient that I estimate makes mistakes, and so I'm actually just going to have an inefficient estimator. The second problem is the one I already mentioned, which is the bias, which is that you might zero out the wrong things. You might zero out things that are confounders. So a group of econometricians published a paper using a very simple method, very easy to implement, that I think highlights some of the intuition for how you might solve the problem and what's wrong with a pure prediction method. So this is a very ad hoc method, but it's something that just gets the main ideas across. So their idea is first you run a lasso of the treatment on x, and you select variables that have non-zero coefficients. So you find all the x's that are related to your treatment. Then you run a lasso to find all the x's that are related to your outcome. Then you say, well, what I really need to control for is the union of those two things. I need to control for things if you're either related to the treatment assignment or related to the outcome. Now, the reason this is kind of ad hoc is that what you'd really, really want to do is find things that are related to both. This is going to control for too much, but it's going to reduce the bias, and they show that this actually works and can get you average treatment effects as long as the model that you're trying to get is simple. So that's a good start. And so some of the things that the cutting edge of this literature is trying to do is to relax some of these sparsity assumptions. So the method that I just described, it only works if the true model is very simple, but you just don't know which covariates are important. So one of the things I've been working on is what if the propensity score, that E hat of x, your probability of getting treated as a function of x, what if that model is actually complex? What if there are lots and lots of websites that place cookies? What if there are lots and lots of signals that determine whether you see an ad? And really ad effectiveness was one of my motivations for this paper. So what we're going to do is we're going to build up from the double robustness literature. So there's a kind of a complicated equation, and I know not even everybody can see the board, but so I'll just try to say it verbally. So the idea of double robust, one way to do double robust estimation is to say my prediction of what would have happened to the treated guys if they had been control is equal to the prediction from a lasso model. So I estimate a lasso or some other regression on the control group. I figure out my prediction function, and then I apply that to the treatment x's. So I say, I build the control model and apply it to the treatment x's. But then I adjust it by something. I take the residuals from that regression, and I add on to that a reweighted average of those residuals, and I reweight those residuals by the inverse propensity score. And so that gives me double robustness, because if I got the model right of what happens in the control group, then those errors on average will be 0. And they'll be 0 no matter how I weight them. But if I made a mistake in estimating my treatment model, then I can still save myself, because if I just rearrange this expression, I can also write the expression as my coefficients from my control model times the imbalance in my x's. So in particular, the propensity weights, what they're trying to do is reweight the x's in the control group to make them look like the treatment x's. And so if I do a good job reweighting my x's so that I make the control group look exactly like the treatment group in terms of their x's, if I do a good job with that, then it doesn't matter if I get the adjustment right, because I'm basically going to have perfectly solved my problem with reweighting. Okay, yep.
Doesn't that mean that if you have, like, say, if you observed only, say, one data instance of a particular characteristic x, so the inverse propensity score would be really high. So that one data point becomes like very
yeah, so a key assumption,
a lot of leverage in that model.
yeah, so a key assumption is you have enough overlap to do this well. But the terrible, terrible thing about this is that trying to estimate a model and then divide by your estimates is like a horrible thing to do, especially if you do it in high dimensions. And it's especially horrible if the model is complex. So what we have a very kind of simple hack to put on this that's going to avoid that step and kind of try to solve that problem. So to do that, I'm gonna write here the mistake I make. So what's the difference between this estimator and the truth? And I can basically write the mistakes I'm making as the product of two terms. It's the product of, did I misestimate my treatment model? And given my weights, did I or did I not reweight my control group to make it look like the treatment group? And so it turns out that you will get the right answer if either you got the coefficient right in the treatment model, in the control group prediction model, or if you reweighted properly. And so now you see, actually, the only thing I need my weights to do is to actually reweight to minimize the distance between the treatment group and the control group in terms of their x's. So our proposed method actually just skips the step of trying to estimate the propensity model, and we just use linear programming to try to minimize the gap between the treatment and control group. And that will then avoid ever dividing by 0 and having a crazy weight. In some sense, the whole point of the propensity weighting was just to get balance between the treatment and control group. And the only reason we did this convoluted thing of first estimating a propensity model and then dividing by it is because beautiful theory from the 1980s told us I could do that in a small data world. And we all got in the habit of doing that. But we never needed to do it to start with. It's just that theoretically it worked as long as you had a zillion data points and no x's. But in the real world, it doesn't work, but you didn't need to do it. So that's our insight. So just solve a linear programming problem. And it's kind of amazing nobody really quite noticed that before. I mean, people kind of did, but this method is new. So, but basically what our proposed method is to estimate lasso or elastic net of y on x in the control group. Then use linear programming to find approximately balancing weights that make the control group look like the treatment group in terms of covariates, with attending to the sum of square of the weights so that you try to make your weights kind of even. And the point is that you can have a little bit of epsilon in that imbalance and it won't totally screw you up. And we actually show that using this method achieves the semi-parametric efficiency bound, which is to say that you actually can't do better than this method in terms of minimizing variance. But the one key assumption is that we do have to have the outcome model be linear. That is, our mistakes are about getting the betas wrong, and if this model is too complicated to estimate, then we're still not going to be efficient. So we do a bunch of simulations to try to assess that. Okay, so you can take a look at the paper. I would say, this is a very active literature, so a bunch of people are coming up with methods. So like, we beat everybody when we came out, and then somebody's coming out with another thing tomorrow, and they're all running horse races. So I don't know that my method will be the winning final method, but I think that the insight that we have about the balancing hopefully will hold up. But I suggest if you were going to try this, you should definitely try different methods and compare them. Okay. So now let me take the last few minutes to talk about treatment effect heterogeneity. And so this is basically, trying to get a personalized estimate for every person. There's actually a lot of different possible questions of interest. Like you could try to find subgroups. So maybe your application wants to come out with different segments that receive different campaigns, and there's a lot of business reasons why you might want segments. I have a paper about that. But I want to talk here about personalized estimates, and I'm probably not going to get to personalized policy estimation, but I have a paper on arXiv about that. So generally, a lot of the early papers bringing machine learning methods to causal inference focused on a single binary treatment in an environment with unconfoundedness. But that's, we saw from Randall that in the advertising effectiveness world, we have a lot of applications of instrumental variables. And so in a recent paper that I have, we call Generalized Random Forest. The point of that paper is to bring some machine learning methods to the instrumental variables world. Randall also was talking about that today, and there's also another paper from a group at MSR called DeepIV, which is a neural nets-based approach. And so we're all kind of pushing in the same direction. So just briefly, actually let me skip over this. So when we think about a popular machine learning method, one is random forests. And so random forests are a popular heuristic for what we call adaptive nearest neighbor estimation. So you can think about a random forest is dividing up a covariate space into blocks, and then what you can do is within a leaf, you're going to make a prediction. So one of the things that we've started to do in causal inference is to say, instead of within a leaf just making a prediction, we might have treated and control observations within a leaf, and so we might actually estimate a treatment effect within that leaf instead of making a prediction. Of course, a random forest is an average of a bunch of those different trees, and those different trees are different from one another because you subsample the training set as well as introduce other types of randomization. So with my co-author, Stefan Wager, who finished his PhD at Stanford last year and now is on the faculty at Stanford in statistics, we proved the first asymptotic normality result for regression forests and also extended it to what we called causal forests. So the basic idea is that random forests can give you unbiased asymptotically normal estimates, and we can actually put a confidence interval around them. We needed to modify random forests in a couple of particular ways, the most important being what we call honesty. So instead of just taking a subsample and estimating a tree and then constructing estimates using all that data, we use what we call double sample estimation. So we use one sample to construct the partition to figure out where to make the cuts. And then we use a second sample of data to estimate the treatment effects within each leaf. And by using independent samples to construct the partition and then estimate the treatment effect within the leaf, we eliminate the bias from random forests that occurs when you use the same data. And in particular, random forests are known to be prone to overfitting outliers and to doing really bad on edge effects. So even in the pure prediction context, it turns out that using honest estimation improves the mean squared error of prediction for those edge cases. And sometimes it does it better on average. So let me skip ahead. And so what the latest work we've been doing is trying to apply these types of methods to a GMM model. So as Randall talked about, in an instrumental variables model, the estimating equation you try to look at is the estimating equation that says that an instrumental variable is orthogonal to the residual from a regression of the outcome on the treatment and the x's. And so the instrument might be something like a randomization that the advertiser introduced. It might be an A/B test that the publisher did. It might be something about the viewability of the ad. And so what we want to do is for instrumental variables regression, we want to figure out how to make the estimates local. And so basically what we do is we use the random forest as a weighting function. So we estimate a random forest, and our splitting rule is targeted towards our goal, which is treatment effects. So we make a split according to whether there's treatment effect heterogeneity, not according to whether the y's are different. And there's a bunch of engineering to make that computationally feasible that we talk about in the paper. But then when we're done with the whole thing, we say if this is our target point x, what we're going to do is go back and re-estimate a model, like an instrumental variables model. But for this target point x, we're going to weight other points more highly if they more frequently showed up in the same leaf in the random forest. So it's really a two-step method where we think of the random forest, instead of actually being a model itself, we think of the random forest as a way to generate a weighting function to estimate a more complicated model. And so the nice thing about this is that actually, from an engineering and implementation perspective, is that you can kind of do this weighting function offline. You can do it in a very computationally expensive way. And then you can use these weights to estimate something, using different data. You can use a different model. You can use a different computational technique. So the idea is I'm really just figuring out, I'm using the random forest to figure out who's your neighbor. I want to compare you to people like you. I don't know who's like you. I have 1,000 different dimensions on which you might be similar. So the random forest is going to tell us who is like you, who are your neighbors. And it's going to make a smooth function of your neighbors, and then you use that weighting function to estimate whatever model you want. So I'm just about over time, so maybe I'll stop there. Just to kind of summarize, maybe there's a lot of contributions from the causal inference and econometrics literature to this problem of advertising effectiveness and generally of doing causal inference with big data. The causal inference literature brings identification and estimation. It tells us conceptually how should we proceed. And it also tells us something about what are the lowest variance ways to proceed. And that's been the focus of econometricians for the past 50 years. But we kind of failed at making things robust, making them systematic, coming up with good ways to validate our approaches. And so that's been a big weakness of this literature. If we bring together the best algorithmic approaches from machine learning for actually doing model selection, but we make sure to tell our machine learning methods what we're trying to do, like we want unbiased estimates, or we want to worry about confounders. We're trying to split on treatment effect heterogeneity, not just on people who look different from each other. We're trying to estimate causal effects. If we bring all those things together, then we can achieve the goals and things we were achieving in the small data literature, but actually achieve them more robustly and reliably. And what's really fun is then that makes us, both allows us to go do things in practice, and it also lets us prove cool theorems and advance the statistical literature. And so I think that's going to be a very exciting area both for theory and practice for some time to come.